During this session, we're going to conclude looking at the non-renewable energy resources available to us with wave power. And we'll look at a few of the slightly different technological developments which are made to harness wave power, and then consider some of the pros and cons associated with this method. So, start off with some of these different methods. The first method is using what's known as a buoyant moored device. Now what we have here is that if we have a device which is floating but held in position, so one part of the device will go up and down with the waves, that energy can be used to create a little bit of motion. That motion in turn, that bobbing up and down, can be used to generate electricity. This is sometimes known as the salted duck. Okay, so it gains energy just by bobbing up and down, and it's constantly going forward, producing electricity, even if it's small values, still working. Next, we've got hinged contour devices. Now, hinged contour devices work with the idea of having long strips, and as the wave motion goes forward, it causes the hinges to go up and down, up and down. They're loosely linked onto the seabed, so let's just look at this in a little bit more detail. So what we have here is that this is an example, and so the long chains of hinged contour devices are all linked together. They're anchored to a position, and as the waves cause sections to go up and down, that snake-like motion going up and down, causes hydraulic rams in each of the links to push forward and backwards, and again causing kinetic energy to be then transferred into electrical energy. Two types. A third type which is available is the oscillating water column. Now what's done here is this is often located against on a shoreline where there's heavy or strong waves, incoming waves coming in constantly. What we have is that the waves coming in, pushing into this system, the waves will cause going up and down through causing a water column to go up and down. This water column, at the top of the water column, there is a section of air, and the motion of the water going up and down pushes air through a turbine and then sucks it back. Pushes it through the turbine and sucks it back. And that motion is constantly tapped in, so the turbine rotates around and causes the generation of electricity. So that's known as an oscillating water column. Three types, all with similar advantages and disadvantages. So advantages are the energy is free, so no fuel is needed, so there's no waste produced. So that means there's no associated greenhouse gases or associated pollutants. Not expensive to operate and maintain. Once they're set up, they will just keep on going and actually can be just kind of left there. They can, by default, produce a great deal of energy. Especially we look at the oscillating water column option. If we have a coastline which is constantly being pounded with big waves, those big waves, if we can tap into that energy, means we can produce quite a lot of energy, especially if it's going constantly. Disadvantages, it does depend on the waves. Sometimes you get lots of energy, sometimes almost nothing. You need to get this right site. A site where waves are constantly strong and you can interfere with either shipping or with flora and fauna. Some designs are thought to be noisy, and put forward as a disadvantages. It has to be said that waves in themselves can produce an awful lot of noise, so this is a problem which can probably be taken with a pinch of salt. So those are the advantages and disadvantages. The other side is that they must withstand rough weather. So, final thing to talk about is that there's a requirement for you to make a calculation of the energy transfer involved in a water wave. This is done through a little bit of simplification. First of all, it's simplified that the idea is that the energy in wave alternates between potential energy as the wave is lifted up and kinetic energy as the wave falls down. Potential energy, kinetic energy, potential energy, kinetic energy. In this diagram, I've created a typical wave. Okay, I have a wavelength. I have the width of the wave, W, the wavelength, lambda, the amplitude of the wave, A, and the velocity at which the wave is traveling. We're going to use these features to try and work out, and I'm going to derive how the power in a water wave is found out. This derivation is just useful because at the end comes a formula, and that formula is just used for that transfer, and that formula is given to you by the IB in the data booklet. So let's start off with this general idea. If potential energy is mass times gravity times height. Height is going to be the average height of the wave, so we're going to consider that to be amplitude divided by 2. Okay. So that's the average height of a wave. So that means potential energy becomes mass times gravitational field strength times the amplitude of the wave divided by 2. If we then take in consideration the density of water, then the mass is going to be density times the volume. As you can see here, what we've done is we've considered, although the wave is not a classical rectangle, it does simplify quite quickly to the idea of being a set volume in a rectangle which has the wavelength multiplied by the amplitude multiplied by the width of the wave. So that gives us another calculation for mass. So potential energy becomes the density times the wavelength times the amplitude times the wave width times gravitational field strength times the new value for height, which is amplitude divided by 2, which in turn simplifies to density times lambda times W times gravity times height times amplitude squared divided by 2. So that's my new potential energy. We have to work a little bit further than that. So, next stage. Power is energy per unit time. So if waves arrive every t seconds, then I can use the idea of the energy transferred, the potential energy, divided by the number of times, the amount of time it takes for a wave to arrive. So therefore I just divide my potential energy by t. In turn, using the wave formula, I know that the period of a wave the wavelength divided by the period gives me the wave velocity. So power becomes density times velocity t times the width times the gravitational field strength times amplitude squared divided by 2. We think about the power per unit length of wavefront, so that means per meter. So therefore I divide by the total wavefront length, which is W, and therefore gives me a value. And this is the formula which is given in the IB textbook or datasheet, and it's going to be a half delta, which is the water density, V is the velocity of the wave, G is the gravitational field strength, and A squared is the amplitude. So with this formula you can do some things. They're going to ask you some questions. So here's a typical question they're going to ask you. Waves of amplitude 1 meter roll into a beach at the rate of 1 every 12 seconds. If the wavelength of the waves is 120 meters, calculate the velocity of the waves, how much power there is per meter along the shore, the power along a 2 kilometer length of beach. So velocity of the waves is going to be 10 meters per second. Okay, because I know the wavelength and I know the period, so wavelength divided by the period gives me 10 meters per second. How much power is there per meter along the shore? So for that I place into the formula which I know, and I come out with 2 times 10 to the 6 watts. Along a length of beach which is 2 kilometers long, what I'm going to do is multiply my value by 2000. So the total power over a 2-kilometre beach is going to be 4 times 10 to the 9 watts. That gives you a full overview of wave power and how it can be utilised and how you can make some calculations about it.